Hi everyone, I'm Kim Channell. I just finished my bachelor's in Earth System Science and Engineering in the Climate and Space Department at U of M. And this fall I'll be returning to U of M to the exact same department for another year to complete my master's in Applied Climate. So appropriately, I'm here today to talk to you about my Great Lakes Hydroclimate project that I worked on this summer under my mentors Chuliang Xiao and Brent Lofgren. So the purpose of this project was to study the regional climate of the Great Lakes region using a downscaled high-resolution model, and one of the sub-goals under this was to examine the differences between future climate change projections for the region. So part of the motivation behind this project, and really this field in general, is the physical uniqueness of our region and the complexities that the presence of the Great Lakes add to our regional climate. So with that in mind, we had a few major points of analysis that we focused on. The first being not just how the lakes respond to global warming, but how they actually interact with the warming temperatures and what kind of effect they might have on the other variables like precipitation and evaporation. And secondly, we focused a bit of our analysis on the effects of decreasing lake ice, because the future projections predict a really heavy decline in lake ice towards the end of the century, and this has big implications for temperature, precipitation, evaporation that are very evident in our results. And lastly, we wanted to examine the responses of precipitation, because it's one of the most complex responses to assess in terms of how it reacts to climate change, and particularly in trying to assess if the presence of the Great Lakes has any effect on it, spatially or temporally. But before getting into the results, there's some background terms and information and a lot of acronyms I have to go over in order for this to all make sense. So first on this list is the Coupled Model Intercomparison Project Phase 5, or CMIT-5. And CMIT-5 is a collection of global climate models and ensembles that provide projections for future climate change under different concentration scenarios set out by the IPCC 2013 Climate Change Assessment Report. And these concentration scenarios are called Representative Concentration Pathways, or RCPs. And these pathways are defined by their corresponding radiative forcing projections by the end of the 21st century. So for example, if you look at the red line in this plot that corresponds to RCP 4.5, that scenario assumes that we reach our peak emissions around mid-century, so we start decreasing our greenhouse emissions around 2050, so that the corresponding radiative forcing trajectory reaches about 4.5 watts per square meter by the end of the century. Whereas the RCP 8.5 scenario in the blue line assumes that we just continue on our business as usual path, and we continue to emit greenhouse gases the way we are now with no counteraction, so that we reach about 8.5 watts per square meters of radiative forcing by the end of the century. So the higher the RCP number, the greater the emissions, the greater the radiative forcing, so generally the more warming to be expected. A global climate model, or GCM, is exactly what it sounds like. It's a climate model that covers the entire globe, but because of its size, it has a very low spatial resolution that can't resolve smaller physical features of a region that are important to its climate, like mountains or lakes. But a regional climate model, or an RCM, covers only a smaller region of the globe, which allows it to have a much higher spatial resolution that can resolve those smaller physical features of a region, but it doesn't have those global circulation patterns in it that a GCM has. It doesn't respond to forcings outside of its own boundaries. So to remedy these drawbacks from GCMs and RCMs, a concept called dynamical downscaling is implemented, and essentially what this does is it uses an RCM to resolve the smaller high-resolution features of a region, but it uses the outputs of a GCM to drive its boundary conditions. So the internal physics of the model come from the RCM, but the inputs at the boundary of the region come from a GCM. The GCM used in this project was GFDL-CM3, which is a global climate model from CMIT-5, but it has such a low spatial resolution of 200 kilometers that it doesn't resolve the Great Lakes, so it doesn't give us a great picture of our regional climate. So it was downscaled with WRF, the Weather Research Forecasting Model, which has a much higher spatial resolution of 30 kilometers, so it can resolve the Great Lakes and can give us a much more accurate picture of our regional climate. The two future climate scenarios that I compared in this project were RCPs 4.5 and 8.5 that I explained on the previous slide, and I generally looked at the last 3 decades of the 21st century, from 2070 to 2100, because the model also ran a historical simulation from 1975 to 2005, so that's about the end of the 20th century, so I wanted to compare it to the end of the 21st century to gauge the magnitude of change that we see in these variables. So now that you have most of the relevant background information you need, I can run you through the methods I used to analyze the climate model outputs that I worked with. So I started by creating seasonal climatologies of all the different variables to look at the spatial distributions of their long-term averages. And then I looked at all the variables on temporal scales to get an idea of how they change over time and a better idea of their seasonality. And then I also did some variability analysis looking at interannual variability, decadal seasonal variability, and I tried my hand at a wavelet analysis, but none of these yielded any striking results. So for the sake of time, I had to cut that out of this presentation. So to ease into the figures and results portion of this presentation, I think this is a good figure to start with. You're looking at lake surface temperatures, climatologies of lake surface temperatures by season. So the season is separated by row or by column, and the scenario is separated by row. So I like this figure because it gives you a really clear view of, one, the differences in seasonal surface temperatures. So you have the colder temperatures in the winter warming up in the spring and summer, then cooling down in the fall. But then you also see the differences between the scenarios. So the warming between the historical scenario and the RCP 4.5 scenario, and then again up to the RCP 8.5 scenario. And they're not even necessarily uniform across all the seasons. You can see just in the wintertime plots that the difference between the average historical surface temperature and the average RCP 8.5 surface temperature is about 6 degrees Celsius, whereas in the fall plots there's only about half a degree difference. So it's not uniform across all the seasons. And part of that big wintertime increase comes from that decreasing ice cover. So the negative values that you see in the wintertime plots are actually corresponding to the temperature of the ice cover over the lakes and not the surface temperature of the water, because water can't be negative degrees, it wouldn't be water anymore. So part of that big increase comes from the fact that there is less ice cover projected for the end of the century in both RCPs, so there's more open water, so there's going to be warmer surface temperatures. And to get a better idea of that, here is spatial distribution plots of the historical RCP 4.5 and RCP 8.5 distributions of ice cover. What you're really looking at here with ice mass fraction is the percentage or fraction of the top layer of the lake that is ice. So the top layer is the top 10 centimeters, so how much of that top 10 centimeters is made up of ice as opposed to water. So you can see that from the historical simulation to both the RCP simulations, there are drastic decreases, especially in the 8.5 simulation. It is a little bit more drastic looking than it actually is because the historical simulation actually overestimates ice cover by a little bit, so those values are a little too high in the historical plot, but it's still a very, very large decrease that we can see effects of in the other climate variables. So this figure is somewhat similar to the first figure, but we're now looking at air temperature at 2 meters instead of surface temperature of the lake. And the bottom two rows are now difference plots, so they're showing you the change in air temperature from that historical simulation to each of the RCP simulations, so that's why the color bars are different from the top plot, so be careful not to mix them up. And you can see in those difference plots in the bottom two rows that all the values are above 0, so it's all positive changes in temperature across the entire region, across all the seasons, but there's significantly greater changes in the winter and summertime temperatures than in the fall and in the spring. And there's also significantly greater changes in the RCP 8.5 scenario than the 4.5 scenario, but that's to be expected. And then up in the top row in the historical simulations, you can see the signature of the lakes in their lag and heat change because of their large thermal capacity. So you can see that in the winter, the lakes and therefore the air right above the lakes are still a little warmer than the air over the surrounding lands. And in the spring and summer, it's the opposite. The lakes are still cold from the winter, but the air is warmer. And then in the fall, the lakes are still warm from the summer, but when that cold air moves in the fall, that's what allows for those great evaporation conditions in the fall. But what's interesting in this figure is that you can also see a signature of the lakes in the different spots. You can see that the colors over the lakes are generally different than the colors over the land. So what this means is that the changes in air temperature over the land are not the same as the changes in air temperature over the lakes, which has significant implications for regional climate change because the lakes have their own role, they have their own interactions with the changing climate. And it's not even necessarily uniform from lake to lake. You can see just looking at the wintertime column in the different spots that the air over Lake Superior in both RCP scenarios increases in temperature more than the air over the surrounding land, whereas the air over Lake Michigan increases in temperature less than the air over the surrounding land. So there's a lot going on here, but it's not uniform over the seasons or even from lake to lake, but there are some significant implications for our regional climate change here and the role that the lakes play in that climate change. So this is a monthly average plot of lake surface temperature. We're back to surface temperature again of just the lakes, and this gives us an additional picture of seasonality a little bit. So you're looking at, on the left, the annual temperature cycle of the historical simulation and the two RCP simulations, and on the right, this is the difference plot, so the change in temperature from the historical scenario to the RCP scenarios. And you'll notice in that right plot that the greatest change in temperature comes in the winter in the month of January, and that again has to do with the declining ice cover and the later half of the century in the RCPs. So you see that in the green line on the left, that corresponds to the historical simulation that it records negative values in the winter, so that's again corresponding to the ice cover over the lakes and not the water. So as the RCPs have more open water, they have higher temperature, so that's where the biggest increase in temperature comes from in the winter. But there's also a smaller increase in temperature in the summer for both RCPs, and this has to do with the stratification of the lakes. So every spring, lake ice breaks up and the lakes reach a temperature around 4 degrees Celsius where they start overturning, and when they stratify, they start this big, sharp increase in surface temperature, and historically that occurred around mid-April on average according to the model. But with less lake ice in future projections, this overturning process appears to occur earlier, which leads to earlier onsets in stratification and earlier temperature increases that allow the lakes to warm even more by midsummer. So this figure is sort of an expanded version of the previous figure. So now you are looking still at lake surface temperature, but you're looking at the months on the y-axis now, so that if you want to see just a yearly temperature profile, you can just look at these plots vertically with the colder temperatures in the winter, warming up in the spring and summer, and then decreasing in the fall. And again, those blue values in this plot are negative, so they're ice cover. And then the x-axis is the year, so you can see how monthly temperature actually changes over time. So I think this plot is interesting because you can see not just how much the temperature values are projected to increase as you go from historical to RCP 4.5 to 8.5 with those deeper red values, but you can also see the length of the warm season increasing. So in the historical scenario, the warmest time of the year for the lakes lasted from maybe July to September, but by the end of the century in the RCP 8.5 scenario over on the far right, that warm season lasts from about June to October, so that's 2 more months of significantly warmer temperatures. And you can also see some of the overturning of the lakes in this plot too, with the green portions of the plots that correspond to that about 4 degrees Celsius mark, where these are the times of the year where the lake stratifies and stratifies. And you can see in this plot, especially in the 8.5 scenario, that the time of year that occurs changes and even grows in length. So fortunately, I don't have time to talk about all of the variables in this way, but it's important to at least touch down on precipitation because it's more complicated in its responses to climate change than temperature is. So these are, again, seasonal climatologies of precipitation over the Great Lakes Basin. And the bottom 2 rows are, again, difference plots, so that's why they have different color bars again. And you can see the signature of the lakes in the historical plots in the top row, with there generally being less precipitation over the lakes than over the land. And you can even see some of the lake effect precipitation in the autumn plot, where those green pockets and all the blue correspond to where the cold air moves over the lakes, picks up the warm moisture and deposits it downwind. But the difference plots aren't quite as well-defined. The most well-defined lake signature in the difference plots is really the decline in precipitation projected over Lake Superior and Lake Erie and Lake Ontario. That's more prominent in the 8.5 RCP. And then the rest of the seasons just generally show increases in precipitation, and you can see a general picture of there being more increases in precipitation over the land than over the lake, but there's nothing particularly prominent here. So this is not everything is quite as simple or neat as temperature change. And then one last figure. This is just, again, monthly averages of precipitation scenarios over the last 3 decades of the 21st century, and then the difference plot, so changes in precipitation on the right. And the most important point to draw from this figure is that big increase in precipitation in the springtime, particularly in the 8.5 scenario. And this corresponds to the time of year when the overturning of the lakes occur. So we saw that that time of year was projected to increase, especially in the 8.5 scenario. And this overturning affects the stability of the water column and the atmosphere above it, so that could have an impact on precipitation, as we can see in this plot. So that was just scratching at the surface of what I did this summer, but in summary, there are clear temperature increases projected for the entire region for all the seasons, but significantly more so for summer and for winter, and also significantly more so for the RCP 8.5 scenario than the 4.5, but that's to be expected because it's almost double the radiative forcing. And there were also distinct hints of a shift in the time of year that stratification of the lakes occur. And unfortunately, precipitation was not quite as neat. There were some general effects of lake signatures, but nothing particularly prominent. And some future work could delve more into the underlying mechanisms of some of these variables and how they respond to climate change, like looking at the overturning process in more depth and examining how the lake atmosphere interactions interact with climate change and the other variables. And in the broader scheme of things, future climate simulations can also be used as inputs for lake level forecasting models in the Great Lakes. So that didn't get to be a part of this project this summer because I just didn't have enough time, but I know that's a very important topic to a lot of people in this lab, so if that is something that is feasible someday, that would be a very useful, vital tool for our region. So that is mostly what I spent my time on this summer. Thank you very much for listening to me talk about it and for providing me this opportunity. It's really meant a lot to me. And I do have some extra slides included if anyone wants to see any additional plots that they were curious about, but I would be happy to take any questions now if anyone has them.
So when you show plots of the historical record and the future scenarios, I'm presuming the historical plots were purely the model simulations, right?
Yes.
Do you have a feel for how well those historical model simulations compared to what we consider to be observations at that time?
Well, I think Andy can answer that better than I can, but yeah, the only one I remember for sure was that the historical ice cover was not completely accurate. Yeah, I'm not sure about the other variables though. So.
I believe you guys use, this is all based on GFDL, right?
That's the GCM used. Yeah.
Do you, based on just your summer experience here, do you have a feel for what would happen with your results if you looked at a broader range of GCMs? Just based on your experience here this summer, would there sort of be an increase in the spread of the results? Would there be a bias? What do you think might happen?
I'm not sure. I know that other global climate models have different spatial resolutions that could affect it, and they have different global circulation patterns and things that they implement. But with using WRF to get that regional picture, I don't know how different it would be. I know, and I read some of the papers where you looked at other GCMs for the Great Lakes, and I know they definitely had some changes, but I don't remember them being all that distinct, so, as far as I know.
So being the doomsday attitude, so let's say we
Yeah.
made some corrections and we changed our rated forcing, and even like your 2.6 model where we've made some changes, and that's sort of the inevitability. You know, we're going to still have this amount of change. Did you also run those comparisons, and you know, like what can we assume that the future is going to look like, even if we make modifications in our greenhouse gas emissions and carbon?
Right, so the 4.5 scenario that I looked at does assume that we make changes so that we stop emitting by about, or we decrease our emissions by about mid-century, and the 8.5 scenario assume that we do nothing. I didn't look at the 2.6 scenario for this project because I don't think it was ever run, so it wasn't available, but I know that scenario assumes that we basically reach our peak emissions right about now, which is essentially impossible, so that it's probably not even a viable scenario to look at. So really the 4.5 is the most reasonable scenario to look at if we can get our act together in the next couple of decades. Yeah.
Any other questions for Ken? So this might be outside the scope of what you were working on because you were doing the analysis and not modeling, but it's relevant. How does work handle the lake surface temperature? Do you prescribe it? Maybe you should answer this. Prescribe it initially, and then it figures the lake surface temperature out to itself.
Yeah, here both is the both lake coefficient. So the lake surface temperature was produced by the lake model. So it's a 1D lake model.
Okay.
So that is the reason why it's not here. So it's already achieved here since there's no lake component in the ETCM. So it's all there. Or it's coupled with the 1D lake model. So all the lake surface temperature and lake ice coverage are from the lake model.
So you're not forced to put it down.